Okay. Okay. So last time we talked about submanifolds of Rn and how if you have a submanifold of Rn, then at any point the tangent space is identified with a subspace of Rn, right? And Rn is equipped with the Euclidean inner product. So restricting the Euclidean inner product to any tangent space of n gives you what's called the induced Riemannian metric, right? So at a point P, GP is the Euclidean inner product restricted to TPM. Okay, cross TPM. Yeah. Okay. And if gamma is a shortest length curve, from its between its endpoints, and if we reparameterize gamma to have constant speed, then gamma satisfies the geodesic equation that the tangential component of gamma double prime is 0, right? Yeah. So this is the geodesic equation. And so this suggests a covariant derivative along curves of vector fields tangent to M along curves. Capital D V dt is the tangential component of the usual derivative dv dt, and this suggests a connection on the tangent bundle so this will go from chi-m cross chi-m to chi-m. Xy goes to nabla xy, which is so you take the derivative of y acting on x and then take its tangential component, right? So here you think of a vector field y on M as a map from M into Rn. Okay, because at each point, Yp is an element of TPM, which is identified with a subspace of Rn. So we can think of Yp as a vector in Rn, right? So any vector field we can think of as a map from M into Rn, and then its derivative dyp becomes a linear map from TPM to Rn. Okay. Is this clear? Yeah. So this was the connection on a submanifold of Rn with the induced metric. And this satisfied two properties. So the main property is the metric compatibility. Which is a vector field X applied to the inner product of two vector fields Y, Z on M, satisfies the Leibniz rule. This is inner product of nabla X, Y with Z plus Y inner product with nabla X, Z. Okay. And the second property it satisfied was the symmetry. Yeah, which said that nabla xy minus nabla yx is equal to the bracket of x and y. Okay, so these two properties, this induced connection satisfies. So then we can now state what's called the fundamental theorem of Riemannian geometry, which says that, so this was, we were talking about submanifolds of Rn, but now we can take a general Riemannian manifold. So Mg is any Riemannian manifold, so not necessarily embedded in Euclidean space. Then the fundamental theorem of Riemannian geometry says that there exists a unique connection nabla on M, which is determined by this metric G in the sense that it satisfies symmetry and metric compatibility. Okay, so when I say a connection nabla on M, what I mean is a connection on the vector bundle Tm, on the tangent bundle. Okay. All right. So the metric determines a unique connection which is compatible with the metric and which satisfies the symmetry property. Okay. So this connection is called the Levi-Civita or the Riemannian connection of the Riemannian manifold. Okay, so is the statement of the theorem clear? Yeah, any questions? Okay, so in the example of a submanifold of Rn, this we have an explicit expression for the Levi-Civita connection. You just take the usual derivative of a vector field in the direction of x and then take its tangential component. This gives the Levi-Civita connection of the submanifold M of Rn with the induced metric. Is that clear? Yeah. Okay, because it satisfies the metric compatibility and symmetry properties. Okay. So I should mention, in fact, it's a famous theorem of Nash. Well, there are two theorems. One is the C1 isometric embedding theorem. And then there is the C infinity isometric embedding theorem. The C infinity isometric embedding theorem says that actually any Riemannian manifold, let's say closed, compact without boundary, can be realized as a submanifold of some Euclidean space Rn with the induced metric. So that means there is a smooth embedding of your manifold into Rn, which preserves lengths of tangent vectors. Okay. So the Levi-Civita connection you can always realize as this particular connection on the submanifold of Rn. Okay. So any questions? Yeah. Okay. So we've seen that when you have a connection on a vector bundle, you get a notion of covariant differentiation along paths. So that we've already seen for general vector bundles. And we've talked about parallel transport along curves, right? So we have parallel transport for the Levi-Civita connection on the tangent bundle. And let me just, so this covariant derivative along curves, I've done this calculation here. You can have a look. It satisfies the metric compatibility of the Levi-Civita connection. It implies that the covariant derivative along curves, it also satisfies a metric compatibility. That is, if I take two vector fields VW along a curve gamma, and I take their inner product, that's a function of the parameter T along the curve. So then ddt of this inner product VW, this satisfies the Leibniz rule. It's the inner product of the covariant derivative dv dt with W plus inner product V with the covariant derivative dw dt. Okay. So in particular, what does this mean? This means that if V and W are parallel vector fields along gamma, then both this dv dt is 0 and dw dt is 0. So that means that ddt of inner product VW is 0. That means that the inner product VW is constant. Right. So parallel transport, therefore, will preserve inner products. So parallel vector fields, the inner product between them will be constant, right? So in particular, their length will be constant and the angles between them will be constant. Okay. All right. So now we can come to the definition of what are called geodesics. So let's just recall that in, so what we want, our geodesics should be shortest length curves in our Riemannian manifold. So we've seen here that for a submanifold of Rn with the induced metric, if I take a shortest length curve, which has constant speed, then it satisfies this geodesic equation, which this is saying that basically the covariant derivative of gamma prime. So gamma prime is a vector field along gamma. This covariant derivative is 0. Okay. Or in other words, the tangent vector gamma prime, this is parallel along gamma, right? Yeah. So this is a necessary condition for a constant speed curve to be of shortest length, right? Is that clear? That is in this induced, in a submanifold of Rn with the induced metric. Now what we're going to do is in a general Riemannian manifold, we will look at curves which satisfy this equation. The covariant derivative of gamma prime is 0. Okay, this covariant derivative of gamma prime, this is, you think of this as the acceleration of the curve. Okay, the acceleration in n. So such curves whose acceleration is 0 will be called geodesics. Okay. So now we have a general Riemannian manifold. So then we say a smooth curve gamma in M is a geodesic if the covariant derivative of gamma prime is 0. Okay. So let's notice some things. So geodesics. So gamma is defined to be a geodesic if the covariant derivative of gamma prime is identically 0. So let's notice that first of all, any geodesic will have constant speed, because if I look at the derivative of norm gamma prime squared, then this is ddt of inner product gamma prime, and by the metric compatibility, this will become twice inner product of d gamma prime dt with gamma prime, and this is 0, right? This, if gamma is a geodesic, so this is 0. So that implies that norm gamma prime is constant. Okay. So any geodesic has constant speed. Okay. And if gamma is a geodesic, and say V is parallel along gamma, then we know that the inner product between V and gamma prime, both of these are parallel along gamma. This is constant, right? So, for example, if I look at a manifold of dimension 2 that is a surface, what that means is if I take a geodesic in a surface and I parallel transport a vector along that, right, then the parallel vector is going to, first of all, the length of the vector will be constant. The length of the parallel vector field will be constant, right? And this inner product with gamma prime will be constant. Therefore, the angle between my vector field V and the tangent vector to the curve gamma prime, this will be constant, right? So along a geodesic, this parallel transport takes a very simple, has a very simple geometric description. You start with any, you see the length and the angle in 2 dimensions, the length and the angle that you make with the tangent vector gamma prime, that will determine the vector V, right? Because we're in 2 dimensions. Yeah. So, if this angle is constant, then we can give, I mean, parallel transport is simply given. If I start with a vector, let's say of length 1, and which makes it an angle theta, then the parallel transport at time t will be given by taking at the point gamma t, you take the unique vector which makes the same angle theta and has length 1, right? That will be the parallel transport. Okay, so that's the name. The reason also for the name parallel transport is that this angle stays constant. So in a sense, you're moving the vector parallel along this curve. Okay. Is that clear? Yes?
Yes, sir, it is clear.
Okay. Okay. Thank you. Okay. So the first thing that we want to see is that this geodesic equation, that the covariant derivative of gamma prime is 0, this should be a second order differential equation, right? Because we're looking at two derivatives. First, we're taking gamma prime and then a second, the covariant derivative. So this should be a second order differential equation. So we should, by the existence uniqueness theorem for ODEs in Rn, we should get unique solutions given two initial conditions, gamma 0 and gamma prime 0, right? Because it should be a second order equation. So let's just see that. So we need to look at this equation in local coordinates. So suppose I take a chart U phi, where phi has components x1 to xn. So then I look at my curve gamma in charts, in the chart phi. So phi composed gamma is some curve in Rn, x1t up to xnt. Then we know that gamma prime t is going to be a sum vi of t of del del xi, where the vi's are nothing but xi prime t. Okay, so vit is xi prime t. And so what will the covariant derivative be? Ddt of gamma prime? Well, we have a general formula for the covariant derivative, right? We got that in terms of the coefficients of the connection or the Christoffel symbols, right? So this will be sum over k, the ordinary derivative, vk prime, plus some terms involving the Christoffel symbols, sum over ij, xi prime, gamma ijk, vj, the whole thing into del del xk. All right. Yeah. So, I mean, this, if I take a vector field, v along a curve gamma, so v is sum over I, vi, del del xi, right? Then what is capital dv dt? So by the Leibniz rule for the covariant derivative, this will be sum over I, vi prime del del xi, plus sum over I, vi into capital ddt of del del xi. So del del xi is a curve on is a vector field on a neighborhood of the curve restricted to the curve. So this will be nabla gamma prime of del del xi, and this nabla gamma prime, that is see, nabla gamma prime, this is nabla with respect to summation vj del del xj. So by linearity, C infinity M linearity in the first variable of the connection, this will be sum over j vj nabla del del xj, right? So here I'll get a sum over I, sum over j, vi, so sorry, nabla gamma prime, this vj is, sorry, this is, sorry, xj prime, sorry, this should be xj prime. Yeah, so this will be xj prime. So this will be vi xj prime nabla del del xj of del del xi, right? And then you use the fact that nabla del del xj of del del xi, this is sum over k gamma ji k del del xk, right? By definition of the coefficients of a connection, right? So once I substitute this in here and then regroup terms, notice one thing, that this nabla del del xj del del xi is the same as nabla del del xi del del xj, because by symmetry of the Riemannian connection, the difference between these two is equal to the bracket of del del xi del del xj, and that is 0, right? Okay, this is 0 because this bracket acting on a function f, that means del squared del xi del xj f minus del squared del xj del xi f. So that is 0 by equality of mixed partial derivatives. Okay, so this bracket is 0. Is that clear? So therefore, by symmetry, this nabla del del xj del del xi is the same as nabla del del xi del del xj. Okay, what that means in terms of the Christoffel symbols is that these Christoffel symbols will be symmetric in ij. Okay. All right. So once you substitute that here, then we get this expression here. Sum over k vk prime plus sum over ij xi prime gamma ij k vj, whole thing into del del xa xk. Then you substitute vj equal to xj prime and vk equal to xk prime. So then this becomes xk double prime plus sum over ij gamma ijk xi prime xj prime, the whole thing into del del xk. So if gamma is a geodesic, then these coefficients of del del xk have to be 0. So that gives you a system of n second order ODEs, right? D squared xk dt squared plus sum over ij gamma ijk of xt into dxi dt dxj dt equal to 0, right? So we see that the geodesic equation, if the Christoffel symbols were identically 0, then this would just be d squared dt squared of xk is 0, and your solution would just be a straight line, right? But in general, the Christoffel symbols will not be 0, so you'll get some nonlinear equation. Okay, this is a nonlinear second order ODE, right? All right. But now, since it's a second order ODE, the existence uniqueness theorem for ODEs in Rn says that given the initial conditions x0 and x prime 0, you will have a unique solution, right? So x0 corresponds to gamma 0 and x prime 0 gives you the value of gamma prime 0, right? So that means, therefore, given any initial condition gamma 0 equal to p and gamma prime 0 equal to some v in TPM, there exists a unique geodesic gamma on an interval minus epsilon to epsilon with these initial conditions, right? Gamma 0 equal to p and gamma prime 0 equal to v, okay, for some epsilon positive. Okay, so what we're getting from the existence uniqueness theorem for ODEs in Rn is that given two initial conditions, p equal to gamma 0 and v equal to gamma prime 0, we have, for a small time, we have a unique geodesic with these initial conditions. Okay. Is this clear? Yes?
Yes, sir, it is clear.
Okay. Okay, so now This is a second order ODE on the manifold M. But you know how to convert second order ODEs to first order ODEs. And when we do that, what will happen is actually this will become a first order ODE in the tangent bundle Tn. So let's see how to do that. So first of all, note, if I have any curve gamma taking values in M, then you have what's called the natural lift of gamma. That will be a curve gamma tilde in the tangent bundle. So gamma tilde of T will be basically the pair gamma T comma gamma prime T. So that's an element of the tangent bundle, right? Gamma prime T is an element of the tangent space at gamma T. So this gives an element of the tangent bundle. All right. So this is called the natural lift. So this is a curve in the tangent bundle. Now, what will happen is that if gamma is a geodesic, then this natural lift gamma tilde will satisfy a first order ODE in the tangent bundle and vice versa. So let's see how to do that. So we need to look at charts on the tangent bundle. So those come from the charts on M, right? So given a chart little phi on M, we get a chart capital phi on the tangent bundle, which sends P together with a tangent vector at P summation Vi del del xi to the point phi P comma V1 to Vn in Rn cross Rn, right? So phi is given by two n coordinate functions, x1 to xn up to y1 to yn, right? From the tangent bundle into Rn cross Rn. So if I look at this curve gamma tilde and apply this chart phi to it, capital phi, I'll get two n functions, x1t, xnt, and then ynt up to y1t up to ynt. And this y1 to yn, these are the coefficients of del del xi, right? So gamma tilde, the vector is gamma prime t. So this will be summation xi prime t del del xi. So that means that the yits will be xi prime t, right? Because gamma prime t is summation xi prime del del xi. Okay, so let me stop this session and start a new one. Okay.
Yeah, it's recording.
Okay. All right. So we see that if gamma tilde is an integral curve of this vector field G phi, then that means that xk prime has to be yk for all k, right? And because the vector field V is summation yk del del xk, that means that V becomes sum over k, xk prime del del xk. In other words, V becomes gamma prime. Okay. So V has to be gamma prime. And the second equation that this dyk dt equal to minus this implies that the covariant derivative of V is 0, right? So V has to be gamma prime and dV dt has to be 0. But that means nothing other than ddt of gamma prime equal to 0. In other words, gamma has to be a geodesic. And the curve gamma tilde, this has to be the natural lift of gamma. It has to be of the form gamma comma gamma prime. Okay, so any integral curve of G phi has to be the natural lift of a geodesic. But the same argument will tell you that any integral of curve of G psi, if I take a different chart psi, then this will also have to be the natural lift of a geodesic. So that means that the vector fields G phi and G psi, they have the same integral curves, right? But if two vector fields have the same integral curves, then they have to be equal, right? Yes, okay, they have to be equal. So that means that G phi is equal to G psi. So that means this vector field is actually well defined, independent of the choice of chart. So actually there is a global vector field G on the whole tangent bundle, which is called the geodesic vector field, such that gamma is a geodesic in M if and only if the natural lift gamma tilde is an integral curve of the vector field G. Okay. So in other words, geodesics in M, you can get as follows. You take an integral curve of the geodesic vector field in Tm and then project it down to M. That will give you a geodesic in M. Is this clear? Yes? Okay. Yes, all right. Okay, so we have this picture where you have your curve gamma taking values in M. Right. And then you have the natural lift, which is a curve in Tm. Okay, so Tm will be a manifold of twice the dimension. So at each point you have the tangent space. Right. And then the natural lift is a curve in Tm. Okay, gamma tilde. This is gamma comma gamma prime. Okay. And here you have the projection. Okay. So this gamma below is a geodesic if and only if this gamma tilde above is an integral curve of the geodesic vector field on the tangent bundle. Okay, is the picture clear? Yes? Yes, is this clear?
Yes, sir, it is clear.
Okay, all right. So now we can treat geodesics as solutions of a first order ODE, okay, by replacing the manifold M with its tangent bundle Tm. Okay. All right. Now let's look at one property of geodesics. So we've already noticed that for a geodesic, the speed, which is the norm of gamma prime, that is constant, right? So geodesics have constant speed. Now, suppose gamma is a geodesic, then for any real number A, let me look at this following reparametrization of gamma. So gamma sub A of t is gamma of AT. The claim is that gamma of AT, this is also going to be a geodesic. Okay, so for that, I just need to check that the covariant derivative of gamma A prime is 0. But what is this? This covariant derivative of gamma A prime, by the formula for covariant derivative this of gamma prime, this is going to be sum over k, d squared dt squared xk of AT plus sum over ij gamma ijk of gamma of AT into ddt of xiat ddt of xjat. Now by the chain rule, d squared dt squared of xk of AT is going to be a squared of d squared xk dt squared at the point AT, right? And similarly, ddt of xi of AT is going to be a times dxi dt at the point AT. So that means from the first term, I'll have an a squared coming out. From here in the second term, I'll have one a from here and another a from here. So I'll also get an a squared coming out. So once I take the a squareds out, what will remain inside is just the covariant derivative of gamma prime evaluated at the point AT, right? Is that clear? Yes? It's just the chain rule, right? It's just the chain rule. An A will come out from here, a from here, and an a squared from here. So you can take that a squared common And then what remains inside is going to be the covariant derivative of gamma prime at the point at. So if gamma is a geodesic, then this d gamma prime dt is 0. So this is going to be 0. So that means that gamma A is also a geodesic, right? Okay. So now we know that a geodesic is determined by its two initial conditions, gamma A of 0, that is also going to be the point P, and gamma A prime of 0. So gamma A prime of 0 by the chain rule is going to be A times gamma prime of 0, right? So if gamma has initial conditions P comma V, then gamma A is going to have initial conditions P comma AV, right? Okay. Is that clear? So what is the point of doing this? The point of doing this is that we can then always reparameterize our geodesic to be defined on a larger interval. So if gamma was a priori defined on the interval minus epsilon to epsilon, then this reparameterization gamma sub A will be a geodesic defined on the interval minus epsilon over A into epsilon up to epsilon over A. Okay, so if I take A to be very small, then my domain of definition for gamma sub A will be large, right? So what does it mean to take A small? That means that the initial condition of this geodesic, gamma A prime 0, which is AV, this vector becomes smaller, right? By a factor of A. So that means if I take my initial vector to be of small length, then it's defined for a larger time, right? So for example, if I decrease the length by a factor 2, then the time gets multiplied by a factor 2. Does that make sense? Yeah? Okay. Right, so the shorter you make the vector, the longer the geodesic will be defined. Is that clear? Yes?
Yes, yes.
Yes, sir, it is clear.
Okay. So why do I want to do this? Because what I want to do is to have geodesics which are defined for time at least 1. I want them to be defined on the interval -1 to 1 at least. Okay, we'll see why. So now suppose let's look at geodesics as solution of a first order ODE in the tangent bundle. So if I take a point in the tangent bundle, theta naught, which is let's say the point P comma is the 0 vector. Okay, so P comma 0, this is a vector in, this is a point in TM. So then we know by the existence uniqueness theorem for ODEs, we have a neighborhood U of theta naught in the tangent bundle such that the flow of the geodesic vector field is defined on this neighborhood U for some fixed epsilon positive, right? Okay. So what that means is that for all points in a neighborhood of theta naught, the integral curves will be defined for the same time epsilon. Okay. Yeah. So what does a neighborhood of this point P comma 0 look like? That means that basically the base point of the tangent vector Q will be close to P. So the distance from P to Q is less than some delta. And also the vector V is going to be close to the 0 vector. So that means the norm of V will be less than some delta. Okay. So I can take this neighborhood to be of this form, Q comma V in the tangent bundle, where distance of P comma Q is less than delta and norm of V is less than delta. Okay. So on this neighborhood, right? So I have theta naught equal to P comma 0 in the tangent bundle. So this theta naught, this belongs to this neighborhood U, okay, where my integral curves are defined for time at least epsilon, okay. So distance PQ less than delta, norm V less than delta. Okay. So this is a open set in the tangent bundle. All right. So here I have phi t the flow of the geodesic vector field defined on U for time mod t less than epsilon. Okay, so what does that mean? That means geodesics with these initial conditions QV are defined for time at least epsilon, right? So for all Q such that distance PQ is less than delta, and for all V in TQM such that norm V is less than delta, right? If I look at the geodesic, so if theta is equal to the pair Q comma V in TM, right? Then geodesic with initial conditions theta, let me call that gamma super theta. So the geodesic gamma theta with initial conditions theta is defined on minus epsilon to epsilon, right? So then if I look at gamma theta of say 80, okay, so this is defined on minus epsilon over A to epsilon over A. So I can make this equal to the interval, let's say minus 2 to 2, if I take A to be half epsilon, right? Okay. So then this geodesic gamma theta of 80 has initial conditions so it starts at the same point Q, but now the vector V has got multiplied by A, right? AV. Yeah. And what is the norm of AV? This is going to be epsilon by 2, that's A, into the norm of V, right? So this is less than delta times epsilon by 2, right? Because norm V was less than delta. So now what does that mean? That means that therefore for all initial condition, let me say theta tilde, which is Q comma W in say U tilde, which is the set of pairs Q comma W. in Tm such that distance PQ is less than delta and norm W is less than delta epsilon by 2. Okay. The geodesic gamma theta tilde, so with initial conditions QW, this is defined on the interval -2 to 2. Right? So in particular, if I take vectors of norm less than this delta times epsilon by 2, so in a small ball around the origin, all my geodesics with those initial vectors are defined for time at least 2, right? So therefore, we can define the following, what's called the exponential map. So this will be defined on a neighborhood of the origin in the tangent space. So first I take for Q in M and this delta and epsilon as above. Okay. Define. Well, okay, then let me take a P and M. Okay, so define. So for P and M, so define the exponential map X sub P. So this goes from a subset UP in the tangent bundle, the tangent space into M. So V maps to. So I have V as a vector in TPM. I take the element of the tangent bundle P comma V. So then I take the unique geodesic with initial conditions P and V, and I flow along that geodesic up to time 1. Okay. So this will be gamma theta of 1, where theta is P comma V. Okay. And what is this UP? This, let's say UP is the set of V in TPM such that if theta is equal to P comma V, then gamma theta is defined on 0 to 1 plus epsilon for some epsilon positive. Okay. So it makes sense to evaluate gamma theta at time 1. Okay. So notice by what we've done above, this ball of radius delta epsilon by 2 is contained inside this set UP, right? So notice that this ball around the origin of radius delta times epsilon by 2, this is contained inside UP. Okay, so this exponential map is always defined on a ball around the origin. Okay. Is this clear?
Yes, sir.
Now, suppose I take a tangent vector v. Okay. So, I let theta be the element p comma v in the tangent bundle. Okay. And so gamma theta is the corresponding geodesic. Right. So what is for t small? I can look at xp of tv. This will be well defined because for t small, the length of tv will become small. It will be contained in a ball around the origin where the exponential map is defined, right? So what is this xp of tv? This means basically I look at the geodesic with initial conditions p comma tv, right? And I evaluate this at 1, right? Yes. Okay. But the geodesic with initial conditions p comma tv is the same as the geodesic with initial conditions pv. And then I take t times whatever argument of this geodesic I'm looking at, right? Yes? Is that clear? Yeah, this is by what we did earlier, what's called the homogeneity of geodesics, right? The geodesic with initial conditions p comma tv, that at a time s is given by the geodesic with initial conditions pv evaluated at t times s, right? Yes?
Yes.
Okay. So that means that this xp of tv is nothing but the geodesic gamma theta of t, right? So therefore, thus, t goes to xp of tv is a geodesic, right? For all. So this is the geodesic. This is the geodesic with initial conditions PV, right? It's given by nothing but xp of TV. So in other words, what that means is if I look at the exponential map, okay, let me draw you a better picture. So let's look at it, for example, for S2. So here is S2. So if I look at the tangent space at the North Pole, that's just this horizontal plane, right? It's just the XY plane. This is my TPN. Okay. This is my point P. So if I take any vector here like this in this tangent plane, right? This is say V, and I look at the straight line passing through V. Okay. So this is the straight line. Okay. So the picture is that if we're looking at say the tangent space to a point in my manifold, I look at all the straight lines through the origin. So those are of the form t goes to tv for some vector v, right? Then these straight lines under the exponential map at p t goes to xp of tv. This will give me all the geodesics passing through p. Right, so in this case, we saw that the geodesics on the unit sphere are great circles. So great circles passing through the North Pole, those will be just all the longitudes. Okay. Okay, so these straight lines are going to map to these geodesics. Is it clear? So here, notice that because my manifold is compact, one can show that geodesics will be defined for all time actually. So in this case, the exponential map will be defined on the whole tangent space, and it will map all of these whole lines to geodesics. And what will happen is that this distance from the North Pole to the South Pole, if this is P and this is Q, this length will be how much? This length will be pi, right? This is length pi. So what this exponential map will do, it will map the circle of radius pi here in the tangent space. So if this distance is pi, this circle will map to a point, the South Pole, right? So xp of norm v equal to pi will be the singleton q. Okay. Is that clear? Yes.
Yes.
Yeah, it's clear. Yeah. Okay. So this is a picture of the exponential map. Okay, so it maps straight lines in the tangent space to geodesics passing, straight lines passing through the origin, not other straight lines, just straight lines passing through the origin. Those will map to geodesics passing through P. Okay. Now, by the existence uniqueness theorem for ODEs, we know that solutions to ODEs depend smoothly on the initial conditions. So that will imply that the exponential map is smooth. Okay. The exponential map is smooth. So we can look at its derivative, therefore, at the origin, at a point, any point. And let's look at its derivative at the origin. So now the origin in the tangent space, because the tangent space TPM is a vector space, the tangent space to TPM at any point, in particular the origin, we can identify with the tangent space itself, right? For a vector space, the tangent space at any point, you can identify with the vector space, right? So then the derivative of the exponential map at the origin, so the origin maps to the point P, right? So the derivative is going to be a linear map from the tangent space to TPM at the origin, that is being identified with TPM, to the tangent space to M at the point P, right, which is TPM. So the derivative of the exponential at the origin, this becomes a linear map from TPM to TPM. And the claim is this linear map is nothing but the identity of TPM. Okay? So the derivative of the exponential map at the origin is just the identity map of TPM. Okay? So why is that? Well, what is the derivative of the exponential map at the origin applied to a vector v? Well, by the chain rule, what you can do is take any curve passing through the origin in the tangent space, whose velocity vector at time 0 is equal to v. So just take the straight line tv. And then by the chain rule, the derivative of the exponential acting on v will be ddt at t equal to 0 of xp of tv. But xp of tv, this is the geodesic with initial conditions p comma v. In other words, the velocity vector of this at time 0 is equal to v, right? So this will give you back v. So that means that the derivative of the exponential at the origin maps V to V. So it is the identity map. Okay. Is that clear? Yes. Okay. So what does that mean? That means by the inverse function theorem, the exponential map will be a diffeomorphism from small neighborhoods of the origin in the tangent space to small neighborhoods of P and M, right? So that you can see in this picture here. If I take small balls in the tangent space, those will map to small spherical balls diffeomorphically in the manifold. Okay, so it will be a diffeomorphism from a small ball here to a small ball here. Okay, a small neighborhood of P here. So now we can make a definition. A geodesic ball B of center P and radius R is the image B equal to XP of B0R of a ball B0R in the tangent space around the origin of TPM, such that the restriction of the exponential map to this ball is a diffeomorphism onto its image. Okay. So the geodesic ball, a geodesic ball around P is just the image under the exponential of a ball around the origin in the tangent space, such that the exponential map restricted to that ball is a diffeomorphism. Okay. And similarly, the geodesic sphere around P is the image of a sphere in the tangent space, such that this sphere is contained in some ball in the tangent space where the exponential restricted to that ball is a diffeomorphism. Okay. So in this picture, the image of small balls in the tangent space here will be these geodesic spheres. Okay. So what are these geodesic spheres in this case? They will be actually nothing but the intersection of the sphere with horizontal planes at some height a bit less than 1. Okay. That will be this intersection. If I cut the sphere with a horizontal plane, I'll get a geodesic sphere like this. Okay. And that will enclose a geodesic ball. Is it clear? So I will have geodesic spheres of radius up to pi, strictly less than pi. So this set here bounded by this small circle here, this whole thing will be a geodesic ball, except when I take length pi, then it will no longer be a geodesic ball because the exponential map will not be a geodesic, will not be a diffeomorphism. Okay. If I take any length bigger than pi, the exponential map will no longer be a diffeomorphism. Right. Is it clear? Yes. Okay.
Yes.
Okay. So now here are some facts which we will not prove. The facts are the following. So now we in fact can say that geodesics will be locally length minimizing. So in the following sense, so if I take a geodesic ball, so this is the image of a ball in the tangent space B0R. Then if I take any point Q in this geodesic ball, so Q is of the form X per V, where norm V is less than R. Then if I take the geodesic from the point P to the point Q, so this geodesic will be gamma Q of T is XP of TV, where T goes from 0 to 1, right? So this will give you a geodesic from P to Q. This geodesic from P to Q, this is contained inside the geodesic ball. This is actually the unique piecewise C1 curve in M of shortest length joining P to Q. Okay. So in this picture, if I take a point, say Q like this, well, I've already got a Q here. So let me draw another picture. So, so I have my tangent space TPM. I have my exponential map XP. And I'm taking a ball of radius R here around the origin. And I'm taking a vector V here inside this ball. Okay. So then I look at the image of this straight line segment, right? Under the exponential map. Okay. So in my manifold, maybe my manifold looks something like this. The image will be a geodesic ball like this. And from P, I'll go to, say, Q. Okay. So the image of this line segment from 0 to V will be a geodesic from P to Q. Okay. And this will be the shortest length curve from P to Q in the whole manifold. Okay. So I have gamma. So I have Q is equal to XP of V, where norm V is less than R. And then I have gamma Q of T is XP of TV, where T belongs to 0, 1. And so this goes from P to Q. And then what I have is that the length of gamma Q, so this is going to be equal to what? Well, remember that geodesics have constant speed, right? So this is integral norm gamma Q prime dt, right? But this has constant speed, so this is equal to the speed at time 0. But at time 0, the initial velocity of this geodesic is v, right? This xtv, its initial velocity is v. So that means the speed is norm v. So this speed is constant equal to norm v. And you're integrating from 0 to 1. So this will be norm v. Okay. And what we're saying is that this is the shortest length curve. So in fact, norm v will be equal to the length of gamma q, which will be equal to the distance between PQ. Okay. So maybe I should write it. Wait 1 second. So let me just. How do I move this? Yeah. Yeah. So, and what is this V? V is equal to the inverse image under the exponential of Q. So this becomes norm of XP inverse of Q. Okay. So that means what? That means the distance from P to Q is nothing but the norm of X inverse of Q. Okay. So you can think of X inverse as a logarithm. So the distance from P to Q is the norm of log Q, where log Q is a vector in the tangent space at P. Okay. So what does that mean? This X inverse is this is a smooth map, and this norm function, this is this norm function is smooth outside the origin, right? So that means this distance from P to a point So this is defined on the ball B, which is the geodesic ball. This is xp of B0R. So this takes values in 0R. This is C infinity on B minus the point P. Okay. And if I square things, then if I look at the norm squared, then that will be the distance of PQ squared. Now notice that the norm squared function, this is given coming from the inner product, right? So the inner product is a smooth function on the vector space. So this norm squared is smooth, okay? So that means that if I look at the distance squared, the distance squared, this is smooth on the whole geodesic ball. Okay, not, I mean, this is smooth at the point P as well. Okay. So is this clear? Yes. Okay. Is this all right?
Yes.
Okay. Okay. So now, here are some more facts. It turns out that the geodesic ball actually equals the metric ball. So remember, Riemannian metric gave you a distance function, right? Which was a metric in the sense of metric spaces, right? The distance PQ was the infimum of lengths of piecewise C1 curves joining P to Q. We saw that that was a metric, right? And the balls for that metric, well, any geodesic ball is a ball for that metric, okay? So of the same radius R, okay, and center P. So the geodesic ball BPR, the geodesic ball B equals the metric ball BPR, which is the set of Q in M, so that the distance from P to Q is less than R. Okay, and the geodesic sphere S equal to X of S0R, this equals the metric sphere SPR, which is the set of Q in M such that distance PQ is equal to R. Okay. So I'm not going to prove these facts. All right. So it turns out, so we saw that for a submanifold of Rn, a necessary condition for a curve to be of shortest length, and if it had constant speed, was that it had to be a geodesic. And so we have a partial converse to that. That is, namely, geodesics are locally length minimizing. So that means that if gamma is any geodesic, if I take any time t0 in the domain of gamma, then there exists an epsilon such that if I take any 2 points st in the interval t0 minus epsilon to t0 plus epsilon, where s is less than t, say, then if I look at gamma restricted to the interval st, then this geodesic, this is the unique shortest curve in the whole manifold M, joining gamma s to gamma t. That means in particular that the distance between gamma s and gamma t is equal to the length of gamma restricted to st. Okay, this equality means that gamma restricted to st is the unique geodesic joining gamma s to gamma t. And what is this length? Well, since gamma has constant speed, this length is just the speed, say c, times mod s minus t. Okay. Okay, so this c is non-gamma prime, which is constant. Okay. Okay, so you can see that in this picture, let's say for S2, if I take these geodesics, then for short times from P to this point, this geodesic is the shortest curve. It's length minimizing. Okay. And in fact, it's going to be length minimizing until I come to length pi, sorry. Until I come to length pi, it will be length minimizing. If I go beyond pi, what happens? If I go beyond pi, then let's say the geodesic will come somewhere here, right? In this case, it's no longer length minimizing, because instead of going this way, I can go backwards and I'll get a shorter curve. All right. So it will no longer be length minimizing after time pi. But for time less than pi, any geodesic in S2 will be length minimizing. Okay. So what this fact is saying is that's true in general. Okay. In general, if I take any geodesic and I take a time T0, then I have an interval around it, T0 minus epsilon to T0 plus epsilon, such that if I take any two times S and T in this interval, then I look at gamma restricted to ST. Okay, then this geodesic gamma joining gamma S to gamma T, this portion, this is the shortest curve in N from gamma S to gamma T. Is this clear? So it is locally length minimizing, but not necessarily globally length minimizing. As you can see in the example of the sphere, right? If I take my geodesics defined on the interval, let's say 0 to 2 pi, then they are not going to be length minimizing. In time 2 pi, in fact, I come back to the starting point P, right? So clearly that's not length minimizing. So yeah, but locally they're going to be length minimizing. If I take any two close enough points on the geodesic, then this geodesic will be the shortest curve between these two nearby points. Okay. Is this all right? Yeah. Yes. Okay. Is it clear?
Yes, sir, it is clear.
Okay, thank you. Okay. So finally, let me just state what's called the Hopf-Reno theorem. So we want a criterion for when geodesics are defined for all time, right? So you can see, for example, if there are sort of holes in the manifold, right? Then geodesics may not be defined for all time, right? So for example, if I take M to be R2 minus a point, minus the origin, let's say, and the G is the usual Euclidean metric, then in this manifold, my geodesics are just straight lines, right? But the origin is removed. So I will, if I take this point, let's say here, like if I take a point P, then the geodesic pointing backwards to towards the origin, it will only be defined for time norm P, right? So, you know, yeah, so this geodesic, if I take it to be of unit speed, then this is a geodesic, this geodesic, this unit speed geodesic only defined on, so if I take it going this way, then on the interval, so up to time norm P, right? And in backward time, it's defined for all time. Backwards, you can go indefinitely, but forwards, you cannot go further, right? Because this origin does not belong to the manifold. So the geodesic will only be defined up to this time, right? So you can see that if the manifold, in this case, what happens is, as a metric space with the induced metric, this manifold is incomplete, right? As a metric space. And that is causing the problem. because of the incompleteness, you cannot extend geodesics further, right? When you encounter a point in the completion which is not in the manifold, right? That's the problem. So what the Hoff-Reno theorem says is that essentially this is the only obstruction to extending geodesics for all time. In other words, if the manifold is complete as a metric space, then geodesics are defined for all time. And actually, this is if and only if. So let me give you the full statement of the Hoff-Reno theorem. So first of all, we say that a Riemannian manifold is geodesically complete if all geodesics are defined for all time. Okay, so for any initial condition PV, if I take the geodesic with initial conditions PV, then it is defined for all time. Okay. Equivalently, if I look at the geodesic vector field on the tangent bundle, that is what we called a complete vector field, right? So its integral curves are defined for all time. Okay. So the Hoff-Reno theorem states the following. So let M be a Riemannian manifold and let P be a point on M. Then the following are equivalent. First of all, the exponential map based at P is defined on all of TPM. That means that any geodesic passing through P is defined for all time. Okay. Secondly, this implies, well, this is equivalent to closed and bounded sets in M being compact. Okay. So you can see that that fails in this example here. In this example, if I take a large enough metric ball around P, then that will be closed and bounded in M. It will be closed in M, right? And bounded, but it will not be compact because it does not contain this origin, right? Okay. So in the setup of the Hoff-Reno theorem, it says that if the exponential map at some point P is defined on all of the tangent space, then that is equivalent to all closed and bounded sets in M being compact. And that is equivalent to the metric space M with the distance function from the Riemannian metric, that being complete. Okay. And that is equivalent to the manifold M being geodesically complete. In other words, all geodesics are defined for all time. So if you look at the last two equivalences, we see that the Riemannian manifold is complete as a metric space if and only if all geodesics are defined for all time. Okay. So that is the statement I was making. And finally, any of these equivalent conditions imply that for any 2 points X, Y, and M, you can join them by a length minimizing geodesic. Okay, so there is a geodesic joining X to Y, which is length minimizing. Okay, in other words, the length of gamma is equal to the distance from X to Y. So in a complete manifold, we can join any 2 points by a length minimizing geodesic. See, again, that is not true if the manifold is not complete. So in this same example of R2 minus the origin, right, if I try to minimize the length from P to minus P, so I'm missing the origin. If I go from, say, P to minus P, right, then I'll get a sequence of curves of shorter and shorter length like this. These lengths will converge to the infimum of all lengths, but the infimum will not be realized by any curve in the manifold, right? You cannot realize the infimum. So the infimum will not be attained. Whereas in a complete manifold, the infimum will be attained and it will be attained by a geodesic. Okay, so the Hoff-Reno theorem also includes that statement. Is it clear?
Yes, sir.
Okay. So in particular, we see from the Hoff-Reno theorem that any compact manifold is well, it's going to be complete, right? Because any compact metric space is complete, and therefore any compact manifold will be geodesically complete. Okay, right? Okay, so any compact manifold will be geodesically complete. Geodesics will be defined for all time. Okay. Okay, so we have a few minutes. Let me just talk a little bit about the next topic. So that will be how to measure volumes on Riemannian manifolds. So for this, let me assume that I have an oriented Riemannian manifold, right? So remember, oriented means I have a choice of orientation on each tangent space, which varies continuously with the point. Okay. So then what can I do? I want to define a volume measure given by integrating some form, some top degree form of degree n, which will be called the volume form. So how do I obtain this volume form? Well, if I take a point P and M, then I look at the tangent space TPM. So this has an orientation and it is an inner product space. So then we already saw when we were doing linear algebra that for an oriented inner product space, such an oriented inner product space has a volume element, right? dvol P. So this is going to be an N form, which is characterized by the property that dvol P applied to any positively oriented orthonormal basis, EI, gives me the value 1, right? Yes? We proved existence and uniqueness of such a top degree form on any oriented inner product space, right? So in particular, we can apply that construction to TPM, right? Yes? Okay. So at each point P, therefore, we will get a top degree form, dvol P. And so that will define an N form, dvol, on my whole manifold. Okay. Which at point P is given by this dvol at P. Is that clear? Yeah. So now we need to see that this volume form is smooth. It's a smooth form. So we need an expression for it in local coordinates. Okay, so let's work out what it looks like in local coordinates. So suppose I take coordinates x1 to xn, which is an orientation preserving chart near P. So then I know that my volume element dvol at P, I can write as some scalar h of P into the top degree form dx1 wedge dxn, right? Because the space of top degree forms is one dimensional, right? So any n form is a multiple pointwise of any non-zero n form, and dx1 wedge dxn is non-zero. So it will be some scalar hp into dx1 wedge dxn. So now let EI be a positively oriented orthonormal basis of TPM. Okay. Then I want to evaluate what is this coefficient h of P. So I can write h of P as h of P into 1, where 1 I write as dx1 wedge dxn applied to del x1 up to del xn. Okay. But now this h of P into dx1 wedge dxn, this is my dvol P. So this I'm applying to del x1 to del xn. Now I can write this as TE1 up to TEN, where T is the linear map from TPM to TPM, which sends the orthonormal basis EI to the basis del xi. So this becomes dvol P of TE1 to TEN. That's the same as T star dvol P of E1 to EN, the pullback. But we know that the pullback of a top degree form by a linear map is just given by multiplying the form by the determinant of T. right? So this becomes determinant of T into d vol P of E1 to En, that is 1. So this becomes determinant of T. So this coefficient H is nothing but the determinant of this linear map T. And how do we work this out? Well, we take the matrix of the Riemannian metric, capital G. That's the matrix Gij. So now Gij is what? It's the inner product between del del xi, del del xj. That I can write as the inner product between Tei and Tej. And that I can write as inner product between T star T of Ei with Ej. But this last expression, this is nothing but the ijth component of the matrix of T star T with respect to the orthonormal basis Ei. In other words, that means that G is the matrix of T star T with respect to the basis Ei. Therefore, the determinant of G is the determinant of T star T, which is the determinant of T whole square. That means the determinant of T is nothing but the square root of G. Okay, so this coefficient H is the square root of determinant G. Okay, so that means our volume form in local coordinates is given by square root of determinant G into dx1 wedge dx. Okay, is that clear? Yes, is that all right?
Yes, sir, it is clear.
Yeah, so that proves that the volume form is a smooth form. Okay. And so then once you have the volume form, you can define the volume of any open set to be the integral of the volume form over that open set. And so that defines a measure, a Borel measure on M, which is denoted by also d vol. Okay. Okay, so let me stop here and we'll continue. Oh, so we won't have classes next week. We'll have the next class will be the week after. Okay. So on the 28th, right? On the 28th. Yeah. So next class will be on the 28th. Okay. So see you then. Yeah. Okay.
Sir, for midterms, see what is the syllabus and the weightage?
Up to the last week, 40 marks. Up to the last week, 40 marks. So this week is not in the syllabus. Okay. Up to the last
Okay,
week.
sir.
Up to vector bundles. Up to vector bundles. And 40 marks. Okay. Okay. Thank you. Bye.